And yes, I just, before we start with the results, can everyone hear me okay? Yes? Okay, good. So before we let Gianpaolo talk about his work, I just wanted to give a few words of introduction about him. So Gianpaolo started working with me in the spring of this year, but in order to secure that project and to really work in the field of supramolecular chemistry, which he's very excited about, he was so keen that he actually reached out to me in September 2021, so 6 months ahead of time, already to secure his project. And we did meet back then, and we discussed a few different projects. And one that caught Gianpaolo's attention the most was actually a different project than the one he will present. It was the one that was related to the recognition of amino acids using crown ether, sugar-based crown ethers. So I have to say I was really happy that I hooked Gianpaolo on sugars, but I had a different idea in mind for him. I actually wanted him to explore a new project that I was just starting to develop, and one that involves self-assembly of chromophore crown ether carbohydrate conjugates, which is what he will present today. And Gianpaolo happily, at least I hope, happily agreed to work on that project. And actually, again, he showed how keen he was, because he already then asked if he could join the lab 2 months in advance to get some more experience working with sugars, which I think it's not a bad idea, because I don't know how many of you know that sugars can be quite tedious to work with and quite problematic. Some people even say working with sugars is like mixing cement. I hope it wasn't as bad for Gianpaolo, and his experience wasn't that bad in the lab with me. And yeah, during the 3 months in the laboratory under my supervision, Gianpaolo worked on preparing and exploring the self-assembly of this new type of carbohydrate derivatives bearing both chromophore and crown ether residues, with the aim of making supramolecular assemblies that could potentially encapsulate and transport cargo in a manner akin to ion channels. He also ventured briefly into the topic of biomolecule co-assembly, studying the assembly of these carbohydrate derivatives with aromatic amino acids and dipeptides. And with that, I'm going to finish, because I think Gianpaolo will tell more about what he was doing, and I'll give the floor to him now.
So, dziękuję, Professor Lewandowski. Thank you very much. And now the floor goes to Gianpaolo for his presentation, please.
Okay. Can you hear me and see? I'm going to share the slides. So tell me if everything is fine. Can you see the presentation?
Yes.
Yes.
I can.
So then let's start. So good afternoon to everyone. As already introduced by Professor Angelella and Professor Lewandowski, the topic of this discussion will be the self-assembly of carbohydrate-crown ether-cromophore systems, or CCCs for brevity, that I explored at ETH under his supervision. Now, to start, I would like to define first what is self-assembly, and it is the spontaneous association of molecules driven by non-covalent interactions to form stable and structurally well-defined aggregates. And self-assembly is actually a very common phenomenon in nature, where we can find many examples of biomolecule-based systems which are able to self-assembly. Famous examples are the DNA double helix formation from the non-covalent interactions between two nucleic acid strands, but there are also many examples of proteins that are able to fold themselves into complex tertiary or even quaternary structures due to non-covalent interactions. So inspired by the power and the versatility of self-assembly, especially based on biomolecules like peptides or nucleic acids, scientists have designed their own synthetic structures out of these biomolecules. And to cite just 2 examples, but there are, of course, many more, I would like to cite the peptides ion channels made by the Gadiri group, which were studied for their ability to serve as channels for potassium or ion or water transportation through cellular membranes. Or in the case of nucleic acids, we have also the case of DNA origami, which are a smart way to design structures that go beyond the simple natural double helix using DNA strands. However, beside peptides and nucleic acids, there is a third class of biomolecules, which is the class of sugars, which possess very interesting features. Indeed, they are widely available biomolecules. They have a very well-known chemistry since they've been studied for centuries. They also are very versatile scaffolds as they possess multiple functionalization sites. And in general, they are also water-soluble and chiral scaffolds. So for these reasons, they've been employed in different fields, ranging from catalysis to chemical biology and also to molecular recognition. And in this latter field, I would like to mention the work done by Dr. Lewandowski on these molecules. So carbohydrate-crown ether systems, which were studied for their ability to act enantioselectively as receptors for amino acids, methyl esters in water, and they were particularly suitable for the recognition of aromatic or hydrophobic amino acids. And however, there is a fourth field that I would like to mention, of course, which is the field of self-assembly, where sugars have been employed. However, especially compared to other biomolecule-based systems, so system based on peptides or nucleic acids, in self-assembly, sugars have not been explored that much, and therefore we have limited examples, and they are mostly hydrogenating materials with some amphiphilic appendages that help this this formation of this kind of materials. So this constitutes a lack of knowledge on both the possible structures and the properties of the materials that we can make out of these sugar-based systems, and therefore they also represent an unexplored potential that we wanted to explore more. So this is why we focused on these CCC systems. As the name may suggest, they are made out of three moieties. We have the sugar, the chromophore, and the crown ether. And the idea came from previous studies on the molecular receptor that I just shown you, which was a sugar crown ether. And the idea was to go beyond molecular recognition by the addition of a third component, which is the chromophore. The chromophore is an aromatic unit, and as such, it's a pi system. And we envisioned that this could be useful for the to drive the self-assembly of such systems through pi-pi stacking. And especially we were interested in these systems because if correctly guided, these structures containing the chromophores, which are basically these big microcycles, could then possibly arrange themselves into structures which have possibly channel-like architectures or in general pores. And we wanted therefore to see if we could employ them as systems for ion transportations or for encapsulation of species. But first we had to study them. And therefore we made, so Dr. Lewandowski has made some preliminary study on this molecule here, and he actually showed that this molecule is indeed capable of self-assembly. This was suggested by NMR analysis, but then it was later proved by TEM. As you can see, this molecule is capable of forming these very long and thick fibers in deuterated water, and these are presumably architectures that are whose construction is driven by pi-pi interactions between the aromatic moieties. So with this in mind, the goal of the thesis was to synthesize these new 4 CCC systems, and we wanted to actually use to synthesize these molecules because we wanted to see if and how small structural changes in these molecules could affect their self-assembly properties. Namely, the difference between compounds 12A and 12B, for example, it's just in the positions of the sugars which are involved in the crown ether ring. For 12A, they are position 1 and position 4, while for 12B, they are position 1 and position 6, while while the difference between compounds 12 and compounds 22, it's in the chromophore, which here it's an anthracene moiety. It's a bigger pi system compared to the naftil for compounds 12A and 12B. So we wanted to synthesize them. We wanted to investigate their self-assembly properties in aqueous media. And also we wanted to investigate their co-assembly properties with some partners. And for partners, we chose aromatic amino acids and the peptides based on the previous results obtained on the molecular receptor, which binded preferentially aromatic or hydrophobic amino acids derivatives. So first we had to synthesize these compounds, and I would like to start with showing the synthetic route to compounds 12A and 12B. This was a synthesis that we adapted from a previous synthetic route that was used in the preliminary study, and the idea was to start from a glucose derivative shown here, which is first protected at position 4 and 6 as an acetonate in the first step. Then we further protect these position 2 and position 3 by benzylation with benzyl bromide. And then we cleave the acetonate under acidic conditions in water to get compound 4. Then, using allyl bromide, we have alkylation of the 3 positions, which are positions 4 and 6. And since they both can react, we actually obtain 2 products out of this step, compounds 5A and compound 5B. These are isomers, and they are actually precursors to the final species 12A and 12B, but at this stage they are not separable, and therefore they were kept as a mixture, and they undergo the other synthetic steps together as a mixture. However, for simplicity, I just show the product of one of the isomer in the following steps. And namely, the following step is first this reaction that serves to start building the chromophore, the crown ether moiety, which is then further expanded by the addition of the chromophore bearing unit, compound 8. Finally, we have the macrocyclization to cross the crown ether ring, and this gives us compounds 10A and 10B that in this step are finally separable by chromatography, and therefore after separation they undergo the following steps individually. And in particular, the following steps are deprotection steps. First, we remove the allyl group, and then by hydrogenation we remove the benzyl groups to give us the final compounds 12A or 12B. So the route instead for compounds 22A and 22B was very similar to those that I've just described, and the only difference being in the chromophore building block, which is not compound 8 but compound 18. Unfortunately, compound 18 it's not commercially available, so we had also to think about the synthetic route for this compound as well. And we came up with this synthetic route, starting from compounds 13 and compounds 14. They undergo a cycloaddition to form this anthraquinone derivative, which is later reduced with sodium borohydrate to the anthracene derivative. Then these methoxy group are cleaved using boron tribromide to give this very reactive species that is called 2,3 anthracene diol. And this is a very reactive species because it's very prone to oxidation. So it has to be immediately protected by a reaction with this component to form compound 18. However, we have had some problems in this with the synthesis of this compound. First, we had problems with the scaling up of the first step, which proved to be more difficult than expected. Then, even if we followed the literature procedure, we could not achieve a full conversion of the conversion from the anthraquinone to the anthracene. So we had actually to optimize from scratch this reaction. And then also the cleavage of these methyl groups proved to be more difficult than expected, and also it was incomplete in most cases. And additionally, we have the intrinsic reactivity of this intermediate, and for all these reasons, we were able to synthesize compound 18, but not insufficient amounts to proceed with the synthesis towards 22A and 22B, which were not synthesized therefore. However, we managed to synthesize compounds 12A and 12B, so the ones bearing the naphthyl group. And as I said before, we wanted to study their self-assembly properties. So starting with compound 12A, which is the 1,4-naphthol system, the first thing that we did was making solutions in deuterated water of these species at different concentrations, from 2.5 millimolar to 5 to 10 millimolar. And we then analyzed these systems by proton NMR. And here, for simplicity, I just show the aromatic portion of the spectrum, which refers to the proton on the chromophore. And as you can see, as we go from lower to higher concentration, these peaks are progressively more shifted towards higher fields or lower ppms, and also they are broader. And both the shifting and the broadening, especially the latter, are hints at self-assembly. However, to prove that we actually have some aggregation, we decided to analyze them by TEM, which is transmission electron microscopy. And the results that we got are shown in this image. In all the samples that we used, regardless of the concentration, we can see these U-shaped structures that we hypothesize are precursors to nanosheets, even though probably they could not have the right conditions to fully develop. Maybe the concentration was too low, but this needs further investigation. Interestingly, though, we also saw just in the sample at 2.5 millimolar the formation of these very long fiber-like structures, which looked promising. Then another thing that we wanted to study was the influence of cations on the self-assembly of this system. And in order to do so, we prepared different solutions at 2.5 millimolar for this species here, and we added to it 5 equivalents of different salts of different cations, from cesium to lithium. The idea was to see whether the presence of these cations could influence the self-assembly, or in general could have an effect on this system, perhaps leading to different geometries, different architectures, or leading not to self-assembling structures, but to discrete structures where probably the crown either could complex the cation. So in order to do so, we did these solutions, and we submit these samples to the proton NMR analysis. And as you can see, in all the cases that we analyzed, all the salts and the cations that we tried, we see shifting and a broadening again of these peaks towards higher fields, except for the case of the potassium-containing solution. And therefore, we have an hint that cations could influence aggregation, but we wanted also to get more insight into this, and therefore we analyzed these samples by TEM again. And in this case, the results are quite different according to the cations that was added. With lithium, for example, we could not see anything in the sample that we analyzed, and therefore we hypothesized that maybe the addition of lithium causes the formation of discrete samples rather than self-assembled species. For sodium, we see this single, in the whole sample, this is the only thing that we observe, single but very long strand. With magnesium, we observe these elliptical shaped objects that we hypothesize are magnesium chloride nanocrystals, but you can see that they are surrounded by more common fiber-like structures, and actually you can see these fibers even without the elliptical shaped objects as well. And with potassium, we observed these lamellar shapes. Then we also wanted to know whether the thermal annealing could have an effect on the outcome of the self-assembly. And for this reason, we annealed samples of this molecule at different concentrations, 2.5, 5, and 10 millimolar. And again, we saw that even after annealing, we have from lower to higher concentration, a progressive shift towards higher fields, and also broadening of the signals, which are again hints at self-assembly. We then also annealed the samples containing the cations, and in this case we see downshifted peaks instead of upshifted peaks, except for the case of the magnesium-containing solution. And then we also studied them by TEM. And what we saw is that after annealing, so before annealing, we had these more or less defined structures, U-shaped, fibers or lamellae, but many more according to the cation that was used or the conditions. But after annealing, we observed random aggregates. And these led us to think that the the structure that we see before annealing are actually kinetically driven. And but of course, we cannot say more about what happens after annealing, because this requires further study. And then we moved to the study of the other isomer, the 1,6-naphtho system 12B. And the first thing that we noticed is that this compound has a lower solubility in deuterated water compared to the previous isomer, since the solution at 10 millimolar is already cloudy. But we repeated the same experiments as before, first making solutions of different concentration containing just a macrocycle and analyzing them by NMR. And again, you see also in this case a progressive broadening and shifting towards higher fields of the peaks of the aromatic protons. And this again, it's an hint at self-assembly. Then we analyze them by TEM. And in this case, however, we just saw random aggregates regardless of the concentration that was used. Then we repeated the experiment with the addition of cations to samples at the same concentration for this new isomer. And we saw basically that nothing changed except for the potassium and the sodium containing solution, which showed a shift of the peaks towards lower fields. And then analyzing them by TEM gave us these results. In particular, for the sodium-containing solution, we have random aggregates again, but for the potassium-containing one, we observed these more defined polygonal shapes, which was quite interesting to observe. And then we moved to another topic, which is the co-assembly studies of these 12A systems, so the 1,4-naphtho system, with one of these co-assembly partners shown here, which are aromatic amino acids derivative. So we chose aromatic amino acids derivatives because we envisioned that the presence of aromatic side chains could be helpful in formation of pi-pi interaction with the chromophore aromatic unit. And we wanted, first of all, to study the co-assembly of such systems, because we envisioned that we could make structures that could benefit from the presence of both sugar-based structures and also peptides. And so what we did was making solutions of this macrocycle and one of the co-assembly partners. For both, we chose the concentration of 2.5 millimolar. And again, we analyzed them first by NMR. We observed that the protons of the chromophore, or at least the peaks corresponding to these protons, appear to be shifted again to higher fields and broaden and appear also to be broader whenever we had the co-assembly partner. So in all cases, we observed broadening and shifting. But also the co-assembly partner is affected because, especially in the case of the tryptophan and phenylalanine containing sample, we also observe broadening and shifting on the protons of the aromatic amino acid side chain. And so again, this is an hint at interactions between these two components, likely occurring via pi-pi stacking between the aromatic moieties of the two components. So then we annealed these samples with the same conditions described before. So we annealed them at 70 degrees for 2 hours, and then we let them cooled down to room temperature. And again, you see that the signals compared to the pure compounds are quite shifted towards higher fields. And also there is an effect on the signals of the aromatic amino acid co-assembly partner, which appears to be broadened. So then we analyzed these annealed solutions with TEM once again, and we had different results in this case as well, with solutions containing phenylalanine enantiomers. So for both enantiomers, we could not observe aggregates. So what we think a possible hypothesis is that the changes in their NMR spectra are due to the formation of discrete species rather than self-assembling structures. Interestingly, though, we also saw that for the tryptophan methyl esters, in the case of both isomers, we observed these spherical shaped structures, while we have nanosheets in the case of the diphenylalanine dipeptide, both in the case of the free C-terminus co-assembly partner, or in the case of the methylated version, which also gave us these very well-defined rectangular nanosheets. And it is worth to mention also that the single components, so the amino acids or the derivatives that I've shown you are not forming these structures without the addition of the macrocycle, or they form different structures. So this is due to the presence of both the co-assembly partners. So to conclude, what we have done is successfully synthesize two new CCC systems. We have shown that small structural changes in the molecule can have a great effect on their self-assembly properties. We studied their self-assembly under different conditions and the influence of different parameters on the self-assembly, with the concentration, within the presence of cations of different salts, and also the effect of annealing. The latter gave us the information that the self-assembly systems that we observed for compound 12A are most likely driven by kinetics. And also we started to study the co-assembly of such systems with amino acids, aromatic amino acids derivatives, even though in this case we need further investigations to get more knowledge on how, for example, this co-assembly is happening exactly. So lastly, I would like to thank a lot of people actually. First, I would like to thank my relator, Dr. Lewandowski, for all the help and everything that he taught me during these months. To Professor Corrà also for being here today as my opponent. I would like to thank Professor Alma Mater for giving me the opportunity to learn a lot about supramolecular chemistry during this experience in her group at ETH. Valtrin Islami for the acquisition of all the TEM images. A huge thanks to all the people from Scuola Superiore of Catania for being just beautiful people and for all the memories that I have there. And I think I will have time to make many more. And a special thanks to Professor Angilella for the support throughout all my journey with the Scuola Superiore, but especially these last days. And to my family and friends as well, I say thank you. And finally, thank you to all the people that are following us today.